Good morning. I'm Suzanne Simard. I'm a Canadian scientist and a forest protector. It is my greatest honor to introduce an international treasure, not just an American treasure, an international treasure, renowned science journalist and New York Times bestselling author Ferris Jabr. Becoming Earth is a literary masterpiece of Earth systems science, how life on planet Earth is highly interconnected and has transformed itself from a piece of rock to a vibrant, living, biodiverse ecosystem, and that we humans are an essential part of this, good and bad. Becoming Earth, what he's going to talk about today, has earned praise such as electrifying, poetic, masterpiece, classic, and it's all true. But I want to talk not just about becoming Earth, but about becoming Ferris. Becoming Ferris began as a boy with his immense imagination about Mother Earth, leading to him coming up with some wonderful hypotheses about where rain came from. This interest, when you talk to Ferris, and I hope you're able to find him and talk to him, you will realize is deeply rooted in him as a person. Becoming Ferris meant earning a Bachelor of Science degree from Tufts University, a Master of Arts in Journalism from New York University. But becoming Ferris, I hope he writes that book, is about guts and tenacity. Let me give you an example. Ferris first contacted me after earning his degree in journalism, one of his first assignments with New Scientist. He wanted to learn about plant communication. Well, this is kind of gutsy for a first-time journalist because that topic has been highly controversial and has been ridiculed roundly by Western science. But he did it, and he talked to me, and he wrote a lovely article called Heard It from the Grapevine in 2011. Then I hadn't heard from Ferris for almost a decade, but in that decade he'd been busy making a big name for himself. He became a contributing writer for the New York Times magazine. He had written articles for the New Yorker, Harper's, The Atlantic, National Geographic, Scientific American, among several other prestigious journals and magazines. He received fellowships and grants, and his writing has been featured in many other series. He's written deeply thoughtful and researched articles with playful titles, such as Can Prairie Dogs Talk? Beauty of the Beasts, Heaven's Microbiome. When Ferris called me again in 2020, he wanted to write an article about my work in the New York Times magazine again. He came up to Canada, and he spent 3 days with me trekking through my experiments, up the mountains, through the clear cuts, in the blazing sun, the pouring rain, with his telltale Write in the Rain notebook, his pocket-sized camera, and his microphone. He took photos, he recorded us digging, swearing, and then cheering when we found those little mycorrhizas. And then months later, he wrote this beautiful article called The Social Life of Forests. Wow, it was a true masterpiece. But here's the thing, when the inevitable backlash arose shortly after, especially after I published my own work, Ferris called me up. He called me to soothe my shattered nerves and discuss how we can deepen this conversation. It is with deep gratitude that I will never forget that heartfelt and much-needed phone call. Not only is Ferris brilliant, he is a truly beautiful human being. Let me introduce you to our international treasure, Ferris Jabr.
Wow. Hello, Bioneers, and thank you, Suzanne, for that extremely generous and lovely introduction. Okay, so my goal today is a modest one, to change the way that you think about the entire world. It's the same goal I had when writing my book, Becoming Earth. The perspective I offer draws on both ancient ideas and modern science. It's really a revitalized, a reinvigorated way of thinking about the planet, not simply as a planet with life on it, but rather as a planet that came to life. My introduction to this way of thinking was an astonishing fact about our planet's largest forest. which is that the Amazon rainforest does not simply receive the rain on which it depends, the Amazon summons that rain. Rain clouds need two essential ingredients to form: water vapor in the air and tiny airborne particles on which that vapor can condense. The Amazon provides both. It pulls huge volumes of water from the soil and releases what it does not use to the atmosphere. In parallel, it's spewing invisible plumes of tiny biological particles that look like this: pollen grains, microbes, fungal spores, even bits and pieces of leaves and insect shells. These little particles, known as bioaerosols, combine with all the water vapor in the air and dramatically accelerate cloud formation. But this giant flying river of water and biology discharged by the Amazon doesn't just stay in place. It moves throughout the continent, bringing rainfall to other parts of South America. And through long-range atmospheric ripple effects, the Amazon even contributes rainfall to places as far away as Canada and the Pacific Northwest. So a tree growing in Brazil can change the weather in Manitoba. Learning to see the Amazon this way, as a massive garden that watered itself, was a revelatory experience for me. Because Western science has long emphasized that life is subject to its environment, not the other way around. Even some of our greatest scientific luminaries, like Rachel Carson and E.O. Wilson, have espoused this view. But the fact that the Amazon generated its own weather and changed weather on other continents made me question that received wisdom. I started wondering how else life dramatically alters its surroundings, not just locally, but on the scale of a continent, an ocean, or the entire planet, and what that kind of profound transformation would mean for our understanding of life and evolution. Seeking answers to those questions eventually took me around the world. I traveled to a remote experimental nature park in Siberia, where Russian scientists are bringing back large grazing mammals to re-engineer the landscape and recreate some version of the ancient grasslands that existed there tens of thousands of years ago during the Pleistocene. I descended close to a mile beneath the surface of the planet in a former gold mine where biologists hunt for bizarre rock-breathing microbes that inhabit and transfigure the planet's deep crust. And I eventually climbed this tower in the heart of the Amazon rainforest, the tallest structure in all of South America, which functions as a scientific observatory literally halfway between the trees and clouds. What I learned is that, contrary to long-standing maxims, life has been a major geophysical force throughout the planet's history, often matching or surpassing the power of glaciers, volcanoes, and earthquakes. Billions of years ago, Earth would have looked like an alien planet to us, with a hazy orange atmosphere devoid of oxygen and a vast greenish ocean pockmarked with volcanic islands but lacking substantial land masses. Microbes, fungi, plants, and animals continually transformed the ocean atmosphere and continents, turning what was once just a lump of orbiting rock into our cosmic oasis. About 2.5 billion years ago, photosynthetic ocean microbes called cyanobacteria began to oxygenate the atmosphere, a long process that was later continued by land plants. In doing so, they gave the sky its familiar blue hue. They formed the ozone layer, and they made fire possible for the first time. Microbes are important participants in numerous geological processes. They carve vast caverns, concentrate precious metals, and they're responsible for most of Earth's mineral diversity. Some scientists think they even played an important role in the formation of the continents. Plankton accumulate in deep-sea sediments that buffer ocean acidification and release gases that increase cloud cover. Animals as diverse as elephants, prairie dogs, and termites continually reconstruct the planet's land surfaces, improving the circulation of air, water, and nutrients. And all manner of life forms collectively converted the planet's once barren crust into fertile soil. But life does even more than just modify the planet's structure and chemistry. Life is also entwined with the planet's capacity to regulate itself. This is one of the primary examples, the planetary thermostat, or the carbonate silicate cycle. And I won't bog us down with too many technical details right now, but the gist is that together, Earth and life, geology and biology, have co-evolved an elaborate process of self-regulation. And it all depends on the element carbon, the element on which all life is based and of which huge parts of our planet are composed. Carbon is continually moving throughout different reservoirs spread throughout the planet. When there's a lot of carbon in the atmosphere, Earth can enter an extreme hothouse state. When there's a lot of carbon sequestered in the deep sea and crust, Earth can freeze. But there's this stabilizing feedback loop built into the system that allows Earth to gradually pull itself back over thousands to millions of years from those extremes. Life has been entangled with that stabilizing feedback and has amplified aspects of it for billions of years. Studying these types of intimate connections between geology and biology brought me to one of the most provocative ideas in the history of Western science, the Gaia hypothesis. Conceived by British scientist James Lovelock in the 1960s and later developed with American biologist Lynn Margulis, the Gaia hypothesis proposes that wherever life emerges, it will inevitably transform its home planet, and that together, Earth and life form a single, self-regulating living entity. One of Lovelock's favorite metaphors for Gaia was a giant redwood tree, because the majority of any mature tree is actually dead wood, which is just laced and ringed with thin strips of living tissue here and there. Similarly, the bulk of Earth is inanimate rock, wrapped in a flowering skin of life. Well, Lovelock argued, just as those thin strips of living tissue are essential to keep a whole tree alive, Earth's living skin helps sustain a kind of global being. Now, while these ideas were immensely popular with the general public when Gaia debuted, the scientific community was harshly critical. When I was in high school and college, I was told that Gaia was closer to mysticism than to real science. And that's in part because in its original articulations, Gaia implied a kind of intent or teleology that contradicted evolutionary biology. Over time, however, Lovelock and Margulis refined their ideas and clarified that their hypothesis did not require any intent or purpose. Gaia was their name for an emergent phenomenon resulting from inevitable interactions between Earth and life. Gradually and quietly, the opposition to the central tenets of the Gaian perspective receded. And today, it's universally accepted within science that life has been a profound geophysical force for at least 3.5 billion years, that Earth and life continually co-evolve, each changing the other, and that together they form a single, tightly interconnected system. Many scientists further acknowledge that life is integral to the planet's self-regulating processes. These ideas have become the pillars of a relatively new mainstream field called Earth system science. Claiming that Earth itself is alive remains provocative, but in my interviews, I've found that many scientists, ranging from chemists to paleontologists to astrobiologists, embrace the notion of Earth as a living planet, and others are increasingly open to that perspective. Even some of Gaia's fiercest original critics, like evolutionary biologist W. Ford Doolittle, have changed their minds in recent years. In the course of writing this book, I've come to see life not as something that simply resides on or inhabits the planet, but rather as a literal, physical extension of the planet. And I like to make an analogy to a vast beach from which spontaneously emerge all manner of intricate sandcastles and sculptures. Just because these structures have attained a new level of complexity and organization doesn't mean they're suddenly divorced from the beach. They're still made of the same grains of sand that surround them. They are still literally the beach. And I think it's exactly the same with Earth and life. Life emerged from and is made of Earth. What we call life is really Earth, animated. Tying this all together, if we accept that life is a literal, physical extension of the planet, that together Earth and life form a single tightly coupled system, and that this greater planetary system demonstrates many of the defining features of life, including evolution, physiology, and perhaps most importantly, self-regulation and astonishing resilience, having endured for more than 4 billion years, then we must recognize Earth itself as the largest and oldest known living entity. Earth may not be identical to an individual organism like a bee or bacterium, but it is meaningfully alive. It's a vast, interconnected living system, suspended in the vacuum of space, eating starlight, radiating song, pulsing, breathing, blooming, and continually defying the forces that would otherwise undo it. And that's exactly what we mean when we talk about life. So how does our species fit into this paradigm? Well, we're the latest chapter in a long saga of life continually transforming the planet. So in that respect, we don't stand out. Yet we are unique because no species before us has so drastically altered so many aspects of the planet in such a short span of time. Some of the biggest changes we've made have occurred in mere centuries. We're also the only species that can knowingly step back and analyze the system as a whole and deliberately alter it. Earth system science clarifies for us exactly how our species has been influencing the planet. We're used to thinking of fossil fuels, for instance, in rather clinical terms as convenient substances or resources available for our use. In reality, fossil fuels represent millions of years of ancient sunlight channeled through the pulsing greenery of life, cooked deep within the planet's crust, and compacted into these ludicrously energy-dense packets of carbon. In fact, a single gallon of gasoline is equivalent to 100 tons of ancient life, or about 20 adult elephants. So think about how much ancient life we're pumping into a single car to keep it running, or how much we use to power the whole world. Our species now emits more than 100 times more carbon to the atmosphere than all the world's volcanoes combined. By unearthing and combusting fossil fuels, we are warping that deep-time carbon cycle that we talked about, that planetary thermostat, hindering Earth's very capacity to regulate itself. In other words, we've pushed the largest living entity into a state of crisis. It's plain that if we want to stop global warming, we have to slash greenhouse gas emissions and stop warping that deep-time carbon cycle. And those emissions come from two major sources: industrial agriculture and food systems more broadly, and fossil fuels and current energy infrastructure more broadly. The Earth system cannot regulate itself fast enough to save us. Its regulation is an extremely slow and gradual process occurring over millions of years, involving a lot of chaos, tumult, and extinction. That is why we are the ones that must reform these systems as rapidly as possible. But there's more that we can do. This kind of thinking underscores the importance of a complementary approach. Our living planet has already evolved many ways of absorbing and storing carbon. We can learn to emulate and enhance those processes. And the best way to do that is to protect and restore the very ecosystems that are already exquisitely adapted to sequestering carbon. Forests, grasslands, peatlands, wetlands, kelp forests, coral reefs, to name just a few. Now, the scale of that challenge is undeniably daunting, but large systemic transformation depends on smaller individual changes. We can all make a difference at a local scale simultaneously. My most personal engagement with such efforts has been through a kind of small-scale ecological restoration and micro-rewilding. One of the chapters in my book focuses on the story of how my partner and I bought a house in Portland, Oregon, inherited this derelict grass lawn, and turned it into a thriving, carbon-storing wildlife garden. It's the story of how we turned this into this. Okay. Thank you. Here's an aerial perspective from the same vantage point, so you can see just how much it changed and filled out in only a few years. And I think the single most important change we made was introducing a large number of healthy and diverse plants to an emaciated landscape. Because once those plants are in place, they initiate an astonishing transformation. Their roots permeate the soil, opening tunnels and circuits for air, water, and nutrients. They attract the symbiotic microbes and fungi with which they co-evolved, and that collectively form the foundation of every terrestrial ecosystem. They help create and maintain soil, which is not just a medium for plant growth, but is itself a living entity with a unique anatomy that must be nourished and protected. And eventually, they attract all sorts of larger wildlife to the garden. When we moved in, all we saw were spiders crawling through the crispy turf grass. Our garden is now routinely visited by a wide variety of wildlife, ranging from glittering green native sweat bees to leafcutter bees, songbirds, hummingbirds, birds of prey, and even mammals like jumping mice and a mischievous family of raccoons that seems to hold some sort of bacchanal in the pond every now and then. To garden is to engage in a form of coevolution, not just with plants and pollinators, but with roots and fungi, microbes and microfauna, with sun and soil. Our garden doesn't belong to just us. It's really a collaboration and a compromise. The idea that Earth itself is a kind of garden is one of the oldest metaphors on record, with numerous iterations in religions and cultures around the world. But the modern scientific understanding of Earth as a vast, interconnected living system reframes that metaphor in an important way. Western science has typically presented Earth as a passive garden, a preformed idol, or a dangerous wilderness that we must learn to shape and tame. In reality, Earth is far from passive. Earth and its constituent creatures are agents in their own evolution. Earth is a garden that sowed itself, watered itself, nurtured itself, and through sentient life forms eventually became aware of itself. A communal garden in whose creation and maintenance every member participates, whether consciously or not. I'd like to close with a quote from one of my favorite writers, Virginia Woolf, whose work I return to frequently for inspiration. And while writing this book, I was astonished to rediscover this passage from her diaries because it was so resonant with everything I'd been learning. Woolf wrote about what she called moments of being, when a deeper truth or reality breaks through everyday perception. In this particular moment, she was looking at some flowers by the door of her family's vacation home in St. Ives, Cornwall. And she suddenly realized that there was this ring connecting the flowers to the earth, and that the real flower, as she put it, was part flower, part earth. And I think that's the gist of what I'm trying to get across. There is this ring connecting us and all life to the planet. And although it's usually hidden from us, we can learn to bring it into glowing focus. Thank you so much.